In this example, we're having a look at solving a system of linear equations. In the first case, we have here two equations with two unknowns, and it's wise to pause here to see if you can solve this system of two linear equations. If you do a process of elimination, you'll find that the two values that work are x equals 3 and y equals 1. And of course, a meaning to that solution is that if we were to graph those two lines, we'd find that they'd intersect at the point x equals 3 and y equals 1. Or alternatively, the value of x equals 3 and y equals 1 are two values that both work in the equations given. Now let's have a look at a system of three linear equations. So this time we have three unknowns, in this case x, y and z. Our plan here is to eliminate one of the variables and to get back to the situation where we have two equations and two unknowns. So let's have a look at the three equations, and what we'll do is we'll try and eliminate x, and we'll do that initially by looking at equations 1 and 2, and we can multiply equation 1 by 3, which means that the coefficients of x are the same. If we then subtract those two equations, we should be able to eliminate x. So in the first instance, what we'll do is we'll go through the operation of taking equation 1, or 3 times equation 1, from equation 2. Again, it would be wise here to check to see that you agree with the coefficients of x, y and z in our resulting equation. So our result from doing that subtraction is 7y minus z is equal to negative 16. Now what we'll do is we'll look at another pair of equations. It could be equation 2 and 3, or it could be equation 1 and 3, and again we'll try and eliminate x. Probably the easiest thing to do is to look at equations 1 and 3. And what we'll do is we'll do equation 3 minus 5 lots of equation 1. That will remove the x value, because we've got a coefficient of 5 in equation 3 and a coefficient of 1 in equation 1. Again, it would be wise to pause here to see if you agree with the calculation that occurs as a result of that subtraction. So the x value is eliminated, and what we get is positive 2y minus 3z is equal to negative 10. Keep in mind to be careful with the subtractions, which result in this case as the positive 2 in front of the y and a negative 3 in front of the z. Again, that can be checked by pausing here to go through those subtractions very carefully. Now we've got two equations, which is taking us back to the original example we had where we've got two equations and two unknowns. And we should be able to solve that for y and z using a simple practice of elimination or substitution. In this case, elimination would be best. We can go through here and look at equation 5 in this case, and equation 4, and probably the easiest thing to do would to make the coefficient of z the same. We can do that by multiplying equation 4 by 3, and then we can do a subtraction. So 5 minus 3 lots of equation 4. Again, it would be wise to pause here to see if you agree with the resulting equation. So looking at our coefficients of y and z, 2y minus 3 lots of 7y means 2y minus 21y. That gives us negative 19y. And negative 3z minus negative 3z is effectively adding, so we get 0z. And in the last set of values, negative 10 minus 3 lots of negative 16 is like negative 10 adding 48, and that gives us 38. So solving that leaves us with y equal to negative 2. We can substitute that back into one of the equations. Probably in this case the easiest one to sub it back into is equation 5. So we substitute a negative 2 where the y is. And what we get is negative 4 minus 3z is equal to negative 10. And we can solve that for z by taking the negative 4 across to the right side. That means we get negative 3z equals negative 6. And then we can divide both sides by negative 3, as we see here in equation 5, to give us z equal to positive 2. So we now have two of the values, y equals negative 2 and z equals positive 2. We can sub that back into one of our original equations that we had right at the start of this problem with three equations. And probably the easiest one to sub it into is the first one we had, which is x minus y plus z equals 5. So we can substitute a negative 2 for y and a positive 2 for z. That means our equation becomes x minus negative 2 plus 2 equals 5, or alternatively x plus 2 equals 5. And if we solve by removing the two values of 2 from the left-hand side, we get that x equals 1. So our final solution to our system of three linear equations is x equals 1, y equals -2, and z equals 2. And we can check that's correct because if we substitute that back into our original equations we had at the start of this problem with three linear equations, each one should be correct.